we are going to pick up where we left off on Friday and talking about rate equations and rate laws and how do we determine them. As a reminder, you have mastering due tonight, which a bunch of you have already started. Awesome and finished. Good job. Also Wednesday night. By the end of today, you should be able to do the homework for Wednesday. No problem. And we'll do another group quiz on Friday. Yeah, because then we have a test coming up. Yay! If you're looking ahead of your calendar, you'll be like, wait a minute, next week is pretty much February. Yep. So. Alright, so let's talk about how do we write rate laws given information, experimental information, given regular information, and how do we predict rates from it. Alright, so I have a reaction between ozone and nitrogen dioxide, which is first order in both nitrogen dioxide and ozone. First question, we want to write the rate equations for this reaction. I will get us started. Good. Super helpful, right? You know what? I'll even throw in this. Alright, looking good. So, what are the reactants for this reaction? NO2 and okay, so those have to be in here. Alright, if I have those two, how do I figure out what the exponents are based on the word problem given? It says first order, so which exponent goes with first order? 1. Good. Success. Thought I'd warm us up with something you feel confident on. Alright, so it tells you it's first order, so the exponents are 1. Good. Alright, so then let's take this rate equation and ask some questions about it. Oh, that should be. Sorry, that should be an NO2. NO2. Alright, so since it's first order in nitrogen dioxide, if I then triple the concentration of nitrogen dioxide, how does that change the rate? It triples also, right? Because it's first order. So if I triple this, assuming nothing else has changed, right? Because I said first order. They're directly proportional. Alright, what about how does the reaction rate change if now I 1/2 the concentration of the ozone? What happens to the rate? Down by how much? 1/2. I see lots of people going like this. Yes, down by 1/2. So that is 2 and 3. If we 1/2 the concentration of ozone, then rate decreases by 1/2 because first order. Alright, fairly good warm-up, right? They're directly related, first order. If you do something to one, it does the exact same thing to rate. Alright, that's where I gave you the orders. What's the one thing about these exponents that we have to be able to do in order to find them? We have to have experimental data. So let's say I have some experimental data. Alright, so here I have a slightly different reaction. Now I have nitric oxide reacting with oxygen to make nitrogen dioxide. I have collected information about I did the nitrogen monoxide at 3 different concentrations. I did the oxygen at 3 different concentrations, and I saw the rate of the reactant disappearing over time. Alright, so let's think about this. Let's say you are in a biology class, which is far-fetched, I know. But let's say you're in one, and you are interested in migration of spiders. I'm not, but maybe you are. Maybe that's your thing, spiders. In which case you keep your experiments away from me because they're gross. So let's say you're looking at migrations of spiders, you know, during the summertime. How do you go about setting up that experiment? What kind of things do you have to keep constant? Right, the type of spider you're looking at has to be a constant. What else do you have to look at? Number of spiders, right? Are you looking at like 1,000 or 10? Are you looking at one moving, whatever it is? Are you going to put like a GPS tracker on one spider and watch it crawl around? So are you looking at, right? You have to hold some things constant in order to measure other things. Because if everything was a variable, you wouldn't have any useful data. Fair enough? The exact same thing here. So I looked at 3 different sets of experiments, right? Experiment 1, 2, 3. Alright, so experiment 1, I had these 2 concentrations. Experiment 2, I had these. Experiment 3, I had these. If I want to compare how the rate is affected by concentration of just this, what do I have to do to this? Hold it constant. Right? Because I want to see how is the rate affected when I change this. Well, then that has to be a constant, because otherwise, if they're both changing, you don't know who to attribute the rate change to. So if I wanted to look at nitrogen monoxide concentration effects, which 2 experiments should I look at? 1 and 2, right? Because the concentration of those 2 are held constant. What happened to the concentration here? By how much? 0.01. Using multiplication, what factor did it change by? 2, right? It doubled. I was at 0.01, now at 0.02. So this doubled. Ooh, there we go. There's no U. There's a U. Doubled. Times 2. Alright, so if my initial rate was 2.5 times 10 to the negative 5th, if it was first order, what number would I multiply it by to get the new rate? Double, right? If it doubled, it would, okay, right? So I doubled here. So it's first order, this rate would have doubled. Did it just double? No. How much bigger is this one compared to that one? What factor? If it's not 2, 4. Right? Because our only options are nothing changes, it doubles, it quadruples. So I doubled the concentration and the rate quadrupled. So what exponent goes with that? 2. Alright, so number 1 goes here. Alright, so I feel pretty good about that. Now I want to look at oxygen. I want to figure out its exponent. Which 2 experiments should I look at to see what just the oxygen does? I heard it. If you do 2 and 3, then both things are changing. 1 and 3, right? For number 1, my concentration of nitrogen monoxide is a constant. What happens to the concentration between 1 and 3? It changed by how much? 2, right? It doubled. What happens to my rate between here and here? Was it the same? It doubled or quadrupled? Doubled. So here, times 2, times 2. Alright, so my concentration doubled, my rate doubled. What exponent goes with that? 1. Now you've done 1 and 2. So you just determined the order, which is those, and now you have the rate equation. So it's second order in NO and first order in O2. Alright, so now I know the orders. I would like, which letter in my rate equation is the rate constant? K. I would like to know K. Which experiment can I determine K from? Trick question. Any of them. You can choose any of them because they all, it's a constant. So for this particular set of experiments, K is going to be the same regardless of which experiment you chose, 1, 2, or 3. Any preferences about what we choose? 1, because we're feeling very straightforward. Alright, so if I choose experiment 1 to determine this, what do I put in for rate? Yep, right there. 2.5 10 to the negative fifth molarity per second equals, okay, K is the thing I'm looking for. Now I plug in that concentration, 0, 1. What do I need to do to that concentration? Square it. And then I plug in that. Let's see here. Oh, forgot my. Yeah. There we go. Alright, so now I did not leave myself enough space to solve this problem. Common issue. Alright, what is that? 0.01 squared times 0.1, so 10 to the negative. Where are the units right now on this side? Molarity what? Cubed. Oh, I was going to say, units in this entire semester are wacky, right? Because this is molarity, this is molarity. So I have squared molarity times molarity. So I have molarity cubed. Yeah, go on. Oh, yeah, 0.01 molar squared times 0.01 molar squared. I'll write bigger, sorry. Alright, so let me scoot this whole thing up. Let's do it like this. So I want to get K by itself, so I'm going to have divide both sides by 1.0 times 10 to the negative 6. Cubic molars. Molars cubic. And that is what now? 0.0. Is that 0? I think I have that wrong. Yeah. That should be 1.5 times 10 to the first. What will be my units on it? Or it could be 25. You can write that as 25. Okay, if I have molarity per second divided by cubic molarity, what cancels out in that fraction? So now I have 1 over molarity squared seconds. So not only is the math algebraically tricky, the units are going to be algebraically tricky. Alright, how do we feel about that? Say that again? Yep, yeah, that'll be fine. Yeah. Yep, certainly. Your choice. Okay, I'll write it bigger down here, right? Because I'm saying it's 2.5 times 10 to the negative fifth. Maybe it's easier if I do it this way. Right, so it's the same thing I have over here. The units are molarity per second. So it's the same thing as molarity inverse seconds. So we're going to cancel out molarity. Yeah. So then, your choice. You could write it like I did. 25, 1 over molarity squared seconds. Or that would be the same as 25 m negative 2 s negative 1. They're the exact same. So, whichever one makes more sense to you, as long as they're right. No, as long as they are correct. I don't care which way it is. They mean the same thing. For me, it's easier because I saw it as a fraction, so I just write it as a fraction. But,
So that won't always.
No, this will only be the units if I happen to have a rate equation that has a second order plus a first order. The units will be different every single time you do a reaction. K is a constant only for one reaction. Yeah. So the units will, so not only, that's what I just said, right? The math is going to be different, and the units will be different every single time. So units are super critical. Yay! You guys look super pumped. Okay, let's do another one.
Yeah.
Let's do another one. Alright, hold on. Let me see if I want to do this one first. Part 4. I'll skip part 4 so we can do more practice problems.
Great.
Yeah. Part 4, you just plug it into the equation you just found. So, alright, I don't want to do the one that's in the PowerPoint next, because that is my challenge problem. We're not ready yet for the challenge problem. Let's do this one instead. Alright, so doesn't even matter. We'll call it A plus B CZ. Alright, so here's the exact same table like I had in the previous one. Molarity of A, molarity of B, and I measured some sort of initial rate for each one of these. Wait for everybody to catch up with you. Ready? Alright, so let's say I experimentally collected this data. Alright, I did 3 experiments. Experiment 1, 2, and 3. I want to determine the overall rate law. Alright, so we're going to start again with rate equals K A B. And we're looking for the exponents. We want to know what is the order of each of these. Okay. Looking at A, which 2 experiments should I choose to see how A affects the rate? 1 and 2, right? Because in this one, what's the relationship between the concentrations? Doubled. Okay. What happened to the rate? It doubled also. So if my rate doubled and my concentration doubled, what exponent do I get? 1. Alright? Which two experiments then should I look at to see about letter B? 2 and 3, right? Because in 2 and 3, change my color. Okay, what happened to the concentration of B, mathematically? It doubled. Did this double? Did it stay the same? What happened to it? It quadrupled. It's this times 4. Times 4 or nothing. Until we get to the challenge problem. But in general. Ah! I suppose I get to an evil laugh. Do I do one of these? Alright, is that what Mr. Burns says? Yeah. Hold on, wait, 0.007, 4. Oh, sure, 28. Yeah, sorry. I was just doing rant. I was just trying to fool you. Gotcha. Yeah. Yep, I doubled this concentration, but this went up by a factor of 4. Which means it got squared. Okay. Yeah, yeah. Okay. Just I divided this number by that number. Whatever number I got is how much it increased by. For the exponent, if this doubles and that quadruples, it means that really, I just memorized it. If it's 2 and 4, it's a square. If it's 2 and 2, it's a 1. I think it's just easier that way. Hope.
How do you know, like, which out of the three entries of two of the three entries what if we decide to make it
If you look at to look at which
for
A, then nothing happened to the concentration. For A, there is no change in the concentration, but the rate did change. You can't look at, no, you have to see how did A affect the rate. How did changing the concentration of A have an effect on the rate? And if you didn't change the concentration, you don't, you can't make that jump. You would do another experiment because you collected crappy data. Yeah, yeah. Yeah, no, it's always going to be obvious. I'm always going to have like 3 experiments. 2 of which will change for one, 2 of which will change for the other. And then it'll be fairly straightforward. Alright, so now we're ready. Maybe. What is K? Which experiment would you like to look at? 1, 2, or 3? Going 3? We'll do 3. That's cool. Alright, so the rate, we're going to look at experiment 3. So the rate, is this red really obnoxious to look at? It's okay? Okay. More. Yeah, anyone would do. Yep, as long as you pick one row, they'll all give you the same letter K. So, you could certainly be doing a different experiment and double check to make sure I got the math right. Alright, so now I have 0.028 molarity per second equals K times, what is this? 0.20. And then what will be the units on this? Just like the last problem. So either this or alright, everybody at least match up on the math. Okay. We ready for... Yes, okay. In that case, we are ready to be challenged. Maybe. You guys are not exactly instilling confidence in me today, so we'll see. Okay. The more we do it, the better it'll get, I promise. It's just one of these sections where you just keep doing the problems over and over and over and over again. You get the hang of it. Alright. That way, if people are still writing the last one, you can start writing this table. Alright, so let's say I have this reaction I am interested in. A plus B makes C. I want to know what the rate equation is for both A and B. Alright, I'm looking at this. Alright, I'm looking to fill in my exponents. Alright, this is kind of what you guys are going to be doing in lab coming up. So I'm trying to do it today so you're ready for lab this week. Alright, so let's look at A first, right, comes first. What two experiments should I look at for A to figure out its exponent? 1 and 2, alright. What happened to the concentration here? Doubled, right? What happened to the rate? Right, it went up by a factor of 4. So what exponent is that? 2. What happened to my experimenter? They made a little bit of a mistake, but don't worry, we can fix it. If you want to leave it unknown, let's change the data, erase it, and fix it. Let's say you are a scientist with morals, and you actually want to use the data you collected. We can still solve it. But right, the issue is is there any obvious relationship between the concentration of B and rate? Not really. They didn't hold anything constant. That's one issue. And is 2.56 any obvious multiplier of 2? But I didn't hold any of them constant. That's what we're going to do. That's what we're going to do. Yeah. Wait, no, she's on it. We could certainly graph it. That would be amazing. We're working up to that. All right, I just rewrote it on a big old sheet. I skipped 2 pages because you guys should have done that as your pre-lab or post-lab. One of your worksheets you did in lab with logs, natural logs, base 10 logs. Right, you did all this. Base 10 logs, natural logs. You did all that. You did your log rules where a multiplication is the same as an addition. Yes, you did that. I know for sure you did that at the very first lab this semester. We didn't used to do that. So that's why it's in my notes. But I feel confident that you guys... No. Alright, so we're going to do exactly what Chandler suggested. We're going to look at how the relationship between 2 rates change things. Alright, Let's see if I can get this all on one screen. Okay, that's close. Right, we're looking for this. Right, looking for the X. We know, let's look at run 1, right? I know concentrations and this rate. Right, I did this, I know this. If I look at, I picked 3, you could have done any of them. If I look at 3, I know these concentrations and that rate. What do I know about K for all 3 of these experiments? It is a constant, right? Which means if I know this set of parameters, and I know this set of parameters for this equation, then K won't change. Which means if I do the ratio of the two, a whole bunch of stuff will cancel out and K will be the same. Okay, since K is a constant, since K is a constant, I can look at a ratio of 2 sets of experimental data. Doesn't matter what K is. K is going to cancel out. And I will be left with how to find X by itself. Yay, math. Alright. So, I chose 1 and 3. You could have chosen 1 and 2, 2 and 3, whatever you want. I'm going to look at run 1 and run 3. So, writing in words what I just said. K's will cancel out, right? Looking at these two, concentrations are going to be different and the rates are different for 1 versus 3. But K is a constant, so it doesn't matter what K is. K is gone. So let's plug in the actual numbers from our table. Let's see, for run 1, this is, here's 1, there, 1, Alright, what happens to my units? They all cancel out. Why? What units does X have? No units. Right? Because it's an exponent, it doesn't have units. So all the units will cancel out. Lucky for you. Doesn't matter what the units are. They're all canceled out. So that part should be, you should be released about that. Released? Alright, so I'm going to do this part of the equation first. Write 2.00 times 10 to the negative 4th divided by 2.56 to the negative second. Alright, what is something I can do to simplify all of this over here? Can I do anything with the factors that have an X on it yet? No, I can't do anything with those guys. But I can certainly square this and divide by that squared. Right? Do 0.1 squared, divide by 0.4 squared. You can do that. Alright, what is another simple step I can do to try and get all the x's on one side of the equation and all the other numbers on the other? Divide by, yeah, okay. So 7.8, negative third, divided by 0.05. I realize I'm carrying out all significant figures. We'll do some rounding at the end. It's just the sig-fig rules are real funky when we do exponents. Just carry them all out, and then we'll simplify at the end. For those of you who are concerned about significant figures, which is probably no one in here. But if you were, I just explained why. Alright, what can I now do with this stuff in the parentheses? I can take the x to the outside and then divide those two. Okay? I'm just going to go ahead and carry on my thought right here. Alright, this is where what you did in lab the other week should come in handy. I want to get the exponent out of the exponent position. Log! So we're going to take a log of the entire equation. So we're going to do log 0.1248 equal x log 0.5. Ugh! We're so close. I can feel it. Right? The x is by itself. Not as an exponent anymore. Just a regular old number hanging out. Just, yeah, waiting to be solved. Anticipating the solving. Alright, what do I need to do now? Yeah, just divide over. So you can either solve both of these and divide, or divide, however you want to do it. At this point, just get the x by itself. Let's see what this is. Log of that. See, what looks super tricky was really just a little bit of algebra. Not terrible. We'll say for this class. Not in reality. For this class, the exponents will always be whole numbers. Until you take more chemistry. Okay. At which point, again, what I've told you in here is like the basis. When we get to like other crazy subjects. Organic doesn't have any math in it at all. It's number free. It's all drawing and all thinking about things in your head. It's like picturing a molecule, thinking about how it interacts with other molecules, and then drawing the correct new thing. So if you are a picture person, then there you go. Oh, which, by the way, organic will be 1 and 2 will be offered over the summer. So as you're planning out your schedule, organic 1 and 2 with labs will be offered over the summer here at Berry College. Yes. So, food for thought as you were thinking about your schedules. Alright, so that's everything I could possibly do with rate exponents solving for that. Right? That's all the different combinations. Either you're going to see it from the table and it's going to be an exponent of 0, 1, or 2, or it's going to be less obvious and then you just do the ratios and you find what x is. So the question should be now, what do I do with all this fascinating information? We will make some graphs! Yay! I'm so excited. As I was sitting in econ again today, because, you know, I do love sitting in econ, they were doing graphs, and I was like, yay! Alright, so if we are looking at a reaction, most of the time you want to know either how long you have to let it sit to let it go to completion, or if I stop it after 30 minutes, how much product have I made, or how much reactant is in it. You're looking at some sort, like, to be honest, you're seeing, can you go get a snack and be back in time? Or do you have to let it go overnight? Right, that's the kind of questions you're setting yourself up for. Most of my concerns are around food, to be honest. I have to figure out when I'm going to eat, what I'm going to eat, how much I should eat. So, which is why I now have a personal trainer who's trying to keep me on task with my training. So, So the issue is, right, the rate law we just wrote, rate equals K bracket bracket, has no dependence on time, right? There's no functionality of time in that rate law. So these questions can't be answered using just the rate law, unless you wanted to run thousands of experiments and try and figure out how long it takes. You don't have time for that, right? Luckily for you, you got amazing algebra skills by the end of the semester. So, lucky for you, we can describe these using math and graphs. Mathematically and graphically, we can answer these questions. Using just a touch of calculus. Touch. Like sprinkle of calculus. Just a pinch of calculus. Enough to like recognize the integral symbol. Feel like I've seen that? I do know that the big S, scripty S looks familiar. No. Alright, let's say I have, we'll get to this. Alright, let's say I have this reaction, right? A goes to B. And I tell you it is first order. Right? Experimentally I figured it out, it's first order. What exponent should I give it if it's first order? A 1, right? That's my rate law. It's first order. I put the exponent 1. So what we're going to do is look at what's called the integrated rate equation. Integrated meaning sprinkle of calculus. Just enough to get you thinking, man, I wish you would derive the whole thing. Again, come on by. No one ever takes me up on this. We could certainly go from first principles all the way to the equation. I'll give you just the gist of it. Alright, remember that? Where I'm looking at the change in concentration. In order to change in concentration, what 2 points of concentration what one for sure do I have to know? Final and initial, right? Initial and final. Right, in order to figure out the change, you have to know 2 points. Right, in order to also describe it, you have to know the initial time and the final and initial time. Right, how long did it take to change that concentration? Otherwise, there's no big delta. So, skipping the integration and getting right down to the actual integrated rate law. Which kind of log is this one? Natural logs. So this chapter is a mix of base 10 logs and natural logs. Alright, so initial A will always get a 0 as a subscript. So the natural log of A equals negative rate constant. How much time has elapsed? What assumption did I make about my time then? What's the easiest way to start the reaction? That T1 is 0. Right, so anything past 0 is T. Right, that's why there's not a T1, T final. It's because I'm assuming that you started the reaction at 0 time. Right, I didn't do something crazy like wait 10 seconds or a minute and then start the reaction, but have the clock going, unless you have a bad lab partner, which does happen. Be coordinated, like start the clock when they dump it in. So time is just complete time elapsed, and this is the initial concentration of A. So useful for, I'm going to say just 3 reasons, but way more than 3. Right, if you know the ratio of concentrations, initial and final, you could figure out K. If you know K and initial concentration, you know how long to wait to get to the amount you want. Or if you know K and you know T, you can figure out the ratio of concentrations. Which, my last thing today, I want to leave you on the graph. Let's see, do I have it on the next slide? Maybe I just have space for it. Nope, okay. I don't have space for it, so I'm going to flip it over. I'll rewrite my equation, right? This is the one I just wrote. Alright, last thing. Because according to my clock up there, I got 3 minutes. Alright, I have this equation, which looks, hopefully, very similar. I've written in the same form as y equals mx plus b. Right? You have a question, Chris? Yeah. Yeah, no, I now know everything. So what, if I do this, which one of the variables should I put on the y? Right, these line up. So I should put ln of A over here. What should I put on the x-axis? What lines up? Time. Okay, what should the slope be? K, and which direction should it be going if it has a negative sign? Downward. Alright, so that's that. So the slope equals K, the negative sign means go downwards. Where should the line hit on the y-axis? B, which is going to be the ln of initial concentration, which makes sense, right? The highest point on the y-axis should be the most concentrated. As time has gone forward, your concentration decreases using the slope of the rate constant. And your initial time is where it's the highest, which for our, just so everything's going to be 0. In that case, we'll use our graph on Wednesday. Oh, and do some more graphing. And talk about things that aren't first order. Man, I just love kinetics the best.